So good afternoon, everybody, or good morning, or good evening. It depends where you are in the globe. It's my pleasure to give this, let's say, 90-minute talk. I will try to finish it in 1 hour, 1 hour, 15 minutes, and then have some time for discussions and questions. So what I will try to cover, or what I as expected. Oops, hold on a second. Oh, I have to go to the beginning. Oh boy. Okay. Just be patient, you guys. Okay, this is the start. Okay, so what I would like to discuss today, or actually what the learning aims, is that you understand the challenges of the memory testing, and specifically how we started in early 70s, 80s, 90s to today. Was memory testing changing over all the time, or was it the same? We'll see that things have been changing significantly, and we'll also realize that today there is a serious gap. The gap between the abstractions we are using, what we call fault models, because as you can imagine, you cannot go deep in chips, in silicon, and inspect each chip and understand what's the defect and test for it, right? What we do typically, we use abstractions, what we call fault models, and we develop solutions for these abstractions. But it turns out that today, these abstractions are not good enough. Specifically when we consider emerging technologies, advanced technology nodes, but also emerging memories, which have unique failure modes. And I will show you that today's solutions fail to detect these unique failure modes. I will show you this based on real silicon data, which this actually calls for a new testing paradigm. And in my team, we developed what you call device-aware test paradigm. I will show it to you, explain it to you. And this is exactly the paradigm on which we built, or we are building, a startup to commercialize the solution. And I will also show you that this new paradigm really outperforms the commercial existing solutions. So I hope with this lecture you will be able to realize that we are entering, or we have to, given the advanced technology node and the emerging memory technologies, we really need to rethink about the way we use to do memory testing, and that this device-aware test is one of the scenarios that could be used to further improve the outcome and protect quality. So my presentation will have 3 parts. First, I will start motivating the problem, why this is interesting. And then I will go provide you with some basics about memories, because maybe some of you are attending, but maybe you don't have enough background in semiconductor memories. So I will provide you some basics about memories. And then I will go to the beef of the presentation. I will start with introducing some terminology and some notations, such that we will be able to describe the memory test algorithm. And then we'll go through the evolution of memory testing. We'll see that we'll split this in 3 phases and see how things will change from one phase to another phase till today. After that, I will show you, based on real data, where do traditional methods break? What are the limitations, the shortcomings, hence the gap? And after that, I will move to the 3rd component of the presentation, where I will have to show you the newer testing paradigm. That's what we call device-aware test. And then I will demonstrate that on real chips like STT-MRAMs and ReRAMs. These are 2 different memory technologies. Finally, I will give you some future outlook and conclude my talk. And hopefully, I will do this all in whatever, let's say 1 hour from now, and we'll have about 15 minutes for discussion. Okay. So as you know, the memories are everywhere, right? Everywhere there are memories. Actually, the share of the memory on chip has been increasing all the time. And if there is a failure in the memory, which cause could cause what we call silent data corruption. I will come back to that later on. That's a case where you have, for example, a data center running, but there is a faulty chip in data center, but the data center is doing calculations silently without having the user or the owner of the data center realize that there's a faulty chip. It could be dangerous. So a failure in the memory could, for example, cause a system failure, could cause safety issues. And if you have a chip failing in field, in a car, whatever, may cause callback of products. And this is a big issue for companies because it means reputation issue. It means losing a lot of potential market share. So clearly, memories are very important, and we have to care about it. And even though we care about a single failure in a chip, in a memory, if you have 1 megabit memory, 1 bit only failing may cause you troubles, may compromise the whole system performance. So it's very, very important to care about it. Actually, the situation is even the worst. This picture is an old picture from International Roadmap of Semiconductor Technology, but it illustrates the key message. What you see of the years, once we move from one generation chips to another generation, you see that the red color, which is the share of memory within SoC, you see that the share of memory has been increasing over the years. Actually, today is dominating the chip area of SoCs. This means actually that the quality, the reliability, and even the yield of your SoC will be mainly determined or dominated by the quality and the yield of your own chip memory. So it's a very, very important component. The bad thing about this, the larger the memories, the higher the accuracy probability that a fault or a defect may take place in the memory. And you see in the yellow line how the yield of memories go down. What is the yield? If you manufacture a wafer, and a wafer, let's say, for simplicity, consists of 100 chips, and from these 100 chips, only 90 are good chips, we say that the yield is 90%. So the higher the yield, the better for the companies to make money. The lower the yield, the less benefit for the company. Obviously, as you can see, with the memories getting larger to 16 megabyte and 20 megabyte, the yield could reach even down 30%, which is absolutely not acceptable. Hence, we need to do something about it. And the common practice in memories is that we use redundancy. Because a memory, as I will show you, it has columns and rows. So if we can replicate additional rows and columns, and this replicant, let's say, or redundant rows and columns, we will use them in case we have a defect column or a defect row. So even though the initial memory it has, for example, one defect row, that defect row we can replace it with the redundant row, and therefore we can still guarantee 100% yield for the memory. And this is a common practice today in memories. Okay, now, good. So the memory is dominating the area. Memory is very important. Yield is very important. We use redundancy, and of course, we need to guarantee a high product quality. We need then what we call high fault coverage. A fault coverage is how much of faults, let's say, if we have a memory with a population of faults of 100 faults. I'm talking about faults, not about defects. I will come back to this later. So if we have a population of 100 fault models, if I will catch 90 from 100, I will say that my fault coverage is 90%. If I will cover 99 faults from 100, I will say that the fault coverage is 99%. So of course, for high quality, I need high fault coverage, which means I need smart, dedicated test algorithms. And these algorithms should be both high quality, means their coverage should be high, but should be also cheap, low cost. What does low cost mean? Just to give you a feeling, what does it mean? Assume we have a test machine, test equipment, which has a speed of 10 nanoseconds, right? And assume I have an algorithm, a testing algorithm, for which the time complexity is linear, 10n. Linear with the size of the memory, and n in this case, it illustrates the size of the memory. If my memory is only 16 kilobits, which is nothing, or 30, you see how things changes. The test time will be 1.6 milliseconds. If it's 64 kilobits, we are talking about kilobits, not megabytes. We are talking about, in this case, test time 6.5. If I have a test algorithm with a time complexity n square, the test time for 64 kilobit will be 7 minutes. 7 minutes to test only a memory of 64 bits on chip. You can see clearly this is not affordable for semiconductor companies. Hence, we need really to think about how to deliver very time-efficient test algorithms, especially when considering that we have to deal with extremely large memories as today the technology evolves. Okay, that's one aspect. The second aspect, we have to detect realistic faults. And as I will show you later on, we have a defect, which is the real defect mechanism in silicon, and we have an abstraction of the defect. And if there is a gap between the abstraction and the defect, an abstraction is just a model, and a model could be accurate, could be less accurate, could be cover the details, could not cover the details, so it depends on the model. So, but if the model does not really 100% reflect the real defects, we may end not detecting all the defects, and this gives us a serious problem. So we need really to deliver solutions for realistic fault models, and of course, solutions are memory specific, either it's a DRAM or ESRAM or immersion technology, and very important, we have to care also about the stress combinations, and I will come back to this later on. So this was briefly to explain to you the importance of memory testing, but also the requirements when it comes to test solutions. Now I would go briefly on some basics about semiconductor memories. So the first level is what we call the behavior level. It's a memory block, has inputs, outputs, you have some data in, data out, you have some addresses. The address gives you the location where you have to write or from which address you have to read, and you have some control bits that tells you either you to read or write in the memory, and of course data in and data out can be actually bidirectional in order to minimize the number of fields. Here is an example that I took actually from a colleague of mine, Eric Hermanis, and it's as a memory interface. You see, for example, the addresses, you see the data input, you see the clock, you see the select chip select, you see write enable. So you have the power off switch, so you can have different power modes to do, for example, sleep mode, etc. You can have bit writer enable, in order to be able to write some selected bits, not only the whole word, but you can even though write at, or read at the or write at the bit level. You can also test bypass mode. You have a mode in which you will bypass the whole memory. It's another option. So there are different options memory can have. And you see, even though here that this memory has some spare rows, it has a spare rows and spare row enable. As I told you before, that you may memories are today typically they have spare rows and also spare columns sometimes in order to ensure that we get a high yield. If we go now deep inside, we open the memory, you have different blocks, you have the memory array, this is where we store the information, zeros and ones, and you have a range of the periphery around it in order to be able to write it. For instance, if you send an address, this address is split in row addresses and column addresses, and then your data in should go through a write driver, a latch, and then through a write driver, through a multiplexing, and then being written in the array. And of course, you have a control and timing generation that takes the control of everything. So typically, of course, the memory array is about 70% of the whole memory because the periphery is relatively occupies less area as compared with the rest. If you go inside the array, you have the SRAM cell, you have the DRAM cell. SRAM cell is 6 transistor cross-coupled inverter, very expensive, and DRAM is just 1 capacitor. And because you have a capacitor, you can have the information can be leaked, and therefore you need to do the refresh every whatever millisecond, 30 or 60 milliseconds. And obviously that's what you see in your DRAM memories, and this is what you see in your cache memory. You go deep in the periphery, you have different designs. You can have a latch-based simplifier that captures the region. You can have the decoding of the addresses. You can have what you call a bitline keeper that keeps the bit lines all the time a little bit higher. You can have a write there. So there are different flavors of the design just to give you a feeling about the memory system. And you go to the last level, is the layer, the real silicon. And this is typically barely published because this is top secret information. And actually, this is what, at the end of the day, what you will map on your wafer. That's the real pattern that you're going to create on the silicon when you're going to create the chip. And all the defects will take place in the real silicon. And this is an illustration from Global Foundries showing the complexity of today's chips. So what you see now is an illustration for how the chips are complex. What you see now is wiring, different metal layers. And you can imagine these are, we are talking about nanometer scale. All these wires can, transport signals, bits, 0 and 1. So it could be data, it could be control signals, whatever. It could be addresses in the memory, etc. And if only one broken line or a line is affected with something, you may end in a non-working chips. You can clearly see that the complexity of these chips are extremely, very, very high. Good. And something about the terminology. So there is a term called defect, error, and fault model. A defect is something unintended difference between the hardware you would like to manufacture and the real manufactured things. And I will show you one picture very soon. And what is an error or a faulty behavior? Let's say if you have a memory, like here, for example, this is a defect. You see, this is a defect, right? Because here, example, we have an unintended connection between two lines here. Here you have a missing VIA. It should be filled in, but it's not filled in. Here you have an abnormal issue in a metal line. So these are defects. What is an error? A defect may cause a wrong operation. For example, I will read 0 from the memory, but because of a defect, the output value is 1 instead of 0. So we have an error. And what is a fault model? Is an abstraction at the behavior level. For example, I will say the memory is always stuck at 1. I assume if there is a certain defect, the way the memory will behave is that we will have always stuck at 1. So you see, this is just an abstraction which may or may not reflect 100% the different defects that can take place. So if you are lucky, you may catch a defect, but you may just test for stuck at 1, but with the fault model, stuck at 1 always reflects some defects, but we have also fault models that may never reflect real defects. And that's exactly the importance of having accurate fault models when it comes to defect modeling. Okay, now, after the terminology, let's move a little bit now, understand the notation of memories. In a memory, you can do read and write. So write X or read X. And X is the value which could be either 0 or 1. Quite simple, right? You can do either write 0 or read 0. Quite very simple. So, and we can have, for example, a series or a sequence of operation. For example, we can apply to a memory write 1, read 1, write 0, read 0. So let's say, for example, to illustrate how it works, let's say we have a memory which has n cells, right? Cell 1, 2, 3, etc. So what I will do first, I will do write 1 to the cell 1, read 1 to the same cell, write 0 to the same cell, and read 0 to the same cell. So I'm applying this sequence of operation. That's we call it a sequence of operations. I will apply it to cell 1. Once I am done, I will move to cell 2. The same sequence of operation. Write 1, read 1, write 0, read 0. And then I can go through all the memory till cell n. And that's actually the notation we are using. So for the memory, to address the memory, because the array is two-dimensional, so what you can do, you need to address in a certain direction. For example, here we were going from cell 1 to 3. So it's kind of up, going up in linear addressing. But we can, even though if you are doing up, you can go either up in like in that case from 0 to n, but you can also go in down direction. Start with n address, n minus 1, n minus 2 till 0. So either you go up or down. That's one way to apply your operation. But sometimes it doesn't matter which direction you can apply, you can use. So it's irrelevant, for example, for the algorithm. Then we use this notation. It's irrelevant direction. But again, because the memory is two-dimensional, you can choose to go fast row. So you go in a direction in which you change the row frequently. So again, this is a memory array where you have the information, the bits are stored. So I can address the memory in this direction, which means I'm changing the row frequently. We call it fast row. So the address will be 0, 4, 8, C, etc. Or you can go fast column. I will change the column frequently. Then in that case, the up addressing will be 0, 1, 2, 3, 4. Or maybe I can do even the fast diagonal. In that case, it will be 0, 5, A, F, and so on. So there are different flavors of addressing directions that an algorithm can apply. And obviously, and this is also proven in silicon, the way you're going to choose your addressing directions has a large impact on the fault coverage you are detecting. So finally, this is actually what we use for notation. So here is a sequence of operations. Write 1, read 1, write 0, read 0. So the addressing mode we are using is up. So we are counting from 0 to the n, and n is the number of addresses. And we are doing column, fast column. Fast column again, what is fast column is 0, 1, 2, 3. And this notation, we call it a march element. So if you see something like this, it's an addressing with a sequence of operation, we call it a march element. So a march element is nothing else than a sequence of operations which are applied to a memory using a certain address sequence, either up or down, and a certain direction, either fast row, fast column, or fast diagonal. All right. So when you apply an algorithm, we are still actually introducing the basics of memory testing. So when you apply a test algorithm to the memory, you can always increase the voltage or lower the voltage, or increase the speed or lower the speed, or increase the temperature or lower the temperature. So this we call them non-algorithm stresses. And silicon data shows, test results shows that these aspects have a large impact on the fault coverage of the algorithm you are using, which means if you select the same algorithm and you use the same algorithm at high voltage and low voltage, the fault coverage could be different. If you use the same algorithm at high speed or low speed, the result could be also different. The same thing applies for temperatures. So we call them non-algorithmic stress combinations. These are not related to the nature of the algorithm itself, but they are related to the environment, right? The temperature, voltage, etc. But in addition to this non-algorithmic stresses, we have what we call algorithm stresses. And algorithm stresses, for example, data background. As you know, again, the memory is two-dimensional. When I write 0, in reality, I'm writing a word or a byte, right? 0, it's a number of bits, either 8 or 16 or 32. So we have different backgrounds. One is solid, so 0 is a solid 0, so you write 0, write 1, etc. But they can have also what we call checkerboard. So my checkerboard, as you see on the screen, if you have a memory which has 4 bits, right? A word of 4 bits, when I will write 0, it's me say I'm writing 0, 1, 0, 1. When I'm writing 1, which is the complement of 0, I'm writing the complement of the first 0, 1, 0, 1, so which is 1, 0, 1, 0. So we call this checkerboard, right? But we can also have column stripe, another data background we can influence, we can use when we apply algorithm, or even though row stripe. So you see, there are different ways to apply an algorithm. And the question is, if you apply a single algorithm with this different data background, will the fault coverage, will the test result be different? The answer is yes. Is that a theory or real silicon? Real silicon data. I will show you something later on, real silicon data. So also remarkable that the data background you are using has a large impact on the fault coverage. And of course, it's some data backgrounds could be very interesting and very crucial to detect some unique defects or unique faults. And of course, as I mentioned, part of the algorithm stresses is which address direction you're going to use, fast row, fast column, fast diagonal, as I already explained. But also counting method, if it's an app, can I just use linear, like 0, 1, 2, 3, 4, 5, 6? I can do also address complement, where I will jump and do a lot of switching. Like you see here, if you have 3-bit address memory, so you can have all zeros and then all ones and then 0, 0, 1 and the complement. So it's called address complement. I can also do addressing where I have the Hamming distance of 1. So you can think about any counting method you want, as long as you cover the whole space. And of course, the counting method has an impact on how many addresses you generate, and therefore on the total test time, because the number of addresses times the operations, it gives you the total test time of your algorithm. So it's very important to take this into consideration. Okay, now I will illustrate an example, right? How we apply this algorithm. For example, we have a match test. Here you see the match test called maths++. The inventor of this March algorithm is called Van de Goor, who was my promoter. Unfortunately, he passed away. He invented this in 1991. And this March algorithm consists of 3 March elements: the first element, the second element, and the third element. The first element consists of 1 operation, write 0, and it has an up addressing. The second element has 2 operations, it has an up addressing. The third element has 3 operations, and it has down addressing. Let me see if I can pointer. Where is this pointer? Okay. All right. And this algorithm stresses use, for example, column stripe, like you see here. No, not here. There's the complement. I will show you. We use linear addressing and fast route. So assume now this is my memory. Assume we have this memory which has only one column memory, just as an illustration, and it has an addresses from 0 to 13, and I would like to apply this algorithm. So the first thing I will do, I will apply this March element. This March element tells you start from address 0 till address 13, and you apply write 0. So I do write 0, and because I am using column stripe, you see the data background is column stripe, because that's the data background I'm using, because I'm writing 8 bits at the same time. That's my memory width in that case is 8 bits. So the next one, what I will do, I will apply the second March element. Again, it's from 0 to 13. What I will do, I will read and then write the complement. I will read and then write the complement. Read, write the complement. Read, write the complement. Read, write the complement. Actually, thanks to Eric Yarmanis, a colleague of mine from IMEC, who did this nice slide with this animation to make it clearly illustrated. So you see now, I am reading, writing the complement, reading, writing the. I will finish it till the end, till the last address. And then next, what I will do, I will go to the third March element, and here I'm starting from. I'm doing down addressing, so I'm starting from address n. In that case, it's 13, going to 0. What should I do? I will do read, write, read. So I will do read, and then write, and then read. And then I get the same thing, read, write, read. And I'm writing, of course, I am reading, writing, and reading, writing, etc. So at the end, the final, you see, the data are complemented. The final values in the memory will be complemented, because I'm doing read 1, and then we need to write 0. So I'm doing the complement of this column stripe data background till it finishes, right? So that's how it works. So after we understood now the importance of memory testing, we understood the notation, we understood the algorithm stresses, non-algorithm stresses, we know what smart algorithm. Let's now take a look at the evolution of memory testing. So around the first phase of memory testing, we can call it ad hoc test. That's the era of simplicity. It started in early 70s and ended around 1975. At that time, companies were mainly using what we call functional testing. So the concept of fault models was not existing yet. So there are some very popular algorithms, memory algorithms, test algorithms like scan, checkerboard, Galpat, and Walking 1.0. I will show them in the next slides. But typically back then, the memories were very small, so the complexity, the test time was manageable. Starting from late 70s till the late 90s, we moved to the era of March test algorithms. And this is where the concept of fault models were playing a very important role. So people were talking about defects, but talking mainly about what is the best way to model these faults. Once we have the fault models, then we forget about defects and we develop test algorithms for fault models. And because fault models are countable, traceable, we can count them, we can then evaluate the quality of each test solution of the algorithm as compared with these fault models. Does the algorithm detect 5, 10, 100% fault coverage, etc.? These made things measurable. They're very important. Okay, so the beginning of formalization started, right? And most of the algorithms in this era were of linear time complexity. Why? Because the memories are becoming now larger. You cannot not afford using n-square algorithms like Galpat and working. These two algorithms are n-square in time complexity, as I will show you, and this is not affordable, not easy affordable when memories are large. And late 90s till today, we are entering a new era. Even though companies are using the test algorithms, using March tests, it turns out that some good chips were escaping the test program, ended by the customer, and the customer were bringing these chips back to the companies, what we call test escapes, which means all the existing algorithms were or are not good enough, which means there are defect mechanisms which are taking place, and the existing fault models are not good enough to detect them. So some companies, what they did, what we call defect-oriented testing. For instance, what they do the characterization of a device, of a memory chip in that case, and they figure out a certain abnormal behavior. They analyze it, they develop an appropriate test solution, they apply it, they check it, it works, and then they add this test program, the test algorithm to the test program to ensure they detect the upcoming faulty chips, at least the chips which consist of the same defect they analyze. We call it defect-oriented testing. So it's kind of focused, narrow, specialized test algorithms dedicated to detect some observed defects. And of course, in this era and today, low power constraints when testing is very important, because if you're going to test your chip in a mode in which it consumes more power than a normal application, this may damage your chip. So how we can manage this? Also, doing high-speed testing or low-speed testing can help. And very important is the test cost versus the quality. So how much test cost I can put on the table? Can you please put yourself on mute? Okay, thank you. So and another aspect is the trade-off between the test quality and the cost. You cannot test for everything because you have a limited budget. Otherwise, it becomes extremely important. So let's go now through these phases one by one. So this is ad hoc test algorithm. The first algorithm is what you call scan. Actually, you write 0, read 0, write 1, read 1. Everybody can come easily with this algorithm. You see this algorithm has 1, 2, 3, 4 March elements. So you start with the memory. You write zeros in all cells, like what you see here, because assuming we are using solid bit at the background, and then you read them. You write the opposite, you are writing 1, and then you read them, and you are done. So the time complexity of this algorithm is linear, and what is the size? Is 4n. N is the size of the memory, and we have 1, 2, 3, 4 operations. So we say the test length is 4n, and therefore time complexity is linear. And because we have the fault models, we defined them. I did not discuss them in details. For example, in a single cell, there may be up to 12 fault models. Yeah, I don't need to talk about them, but just to give you this fault model are defined, so we can measure how many faults from 12 single cell does this test algorithm detect. Mathematically, we can prove that this guy can detect only 7 from 12. And when it comes to faults involving 2 cells, assume, for example, you access 1 cell, and because you access 1 cell, there is a defect between 2 cells, the other cell will flip from 0 to 1. We call it coupling cell, in which 2 cells are involved. So how many, in theory, static faults? What is static is a fault that takes place or can be activated with at most 1 operation. We don't need that timing and accumulation there. So in theory, you can have 72 coupling faults, and we can easily demonstrate that this algorithm detects only 18 from 72. So you can get a feeling about how good or how bad is the algorithm. You can do the same thing for address decoder faults. You remember the peripheral circuit or peripheral circuit in general. But at least we can measure the fault coverage. Another algorithm, which is a part of ad hoc, is what you call checkerboard. It's quite similar like scan. The only thing it does, it splits memory in 2 kind of cells, I and I plus 1. Let's say when you write the first March elements, what it does, it writes 1 to I cells, and it writes 0 to I plus 1 cells, which means actually for initialization, you get something like this. It's checkerboard. Actually, you are forcing checkerboard, as simple as that. And then what you do, so again, you classify cells in 2 classes, zeros and ones. You write 1 to cells zeros, you write 1 to cells 1, the orange, and you write 0 to cells 2 in this case the green, and then you read them and you write the opposite value. Quite simple. You read and you write the opposite value, and then you read again. So what is the test length again for N? Quite similar to scan. The fault coverage again similar to scan, so quite similar. And this could be very important for DRAMs, because DRAMs, as I told you already, the information is stored in a capacitance, and you can imagine if this is the cell surrounded with all zeros, we can maximize the leakage of this capacitance and therefore accelerate the detection of the fault if there is any fault there. Okay, still within the ad hoc test algorithms, there is what we call gulping or working algorithm. This has been, again, invented in 70s. And to be honest with you, some companies in certain form are still using gulpat and working. Although it's extremely expensive, and I will show you later on why, based on real silicon data. For now, let's take a look how it works. So this is the pseudocode or the algorithm. You start with data, you initiate the data to memory to 0. One time you do it to 0, and then you do the opposite value. Let's start with 0. So initial memory to the 0, right? Okay, so all the let's say the EI in that case is the cells. We have whatever 16 cells. So we initialize all the 16 cells to 0. That's what we did. And then we start from base cell. We start at 0 till 16 in that case, because N we have 16 cells. We start from 0 to 15. Right? So what we do, we start moving the base cell to 1. Let's say we do first column 2, 3, 4, and so on. And once we move the base cell, we perform a read operation. And once we perform the read operation, so what we do, we go to the base cell, we write the complement data. Let's say if it was 0, we write 1. Then we perform a reduction that I will explain in a second. And then after we perform the reduction, we write the opposite data value to the cell. Example, assuming we arrived to the base cell here. What we did, we wrote the base cell to 1, and now we have to start the read value. The gulpat read action, how does it work? It reads non-base cell, base cell. Go to base cell, non-base cell, base cell. It does ping-pong. Read this one and then this one. Read this one and then this one. Each time he reads non-base cell, base cell, non-base cell, base cell. He goes through the whole memory till he finishes. Once he finishes the reduction, we will go back, and then what we do, we write back 0, and then we move to the next action. So this is how gulpat works. For the working, what it does in the reduction, it starts with reading all non-base cells. It bypasses the base cell. It reads the whole non-base cells, and then it goes back and reads the base cell. So the only difference between gulpat and working is in the read action. When it does ping-pong, read base cell, non-base cell, base cell, non-base cell, and when it reads non-base cells completely, and then goes back and reads the base cell. So what's the time complexity? The test length is 4 n squared plus 2n, which means the time complexity is n squared. And remember, in the table I showed you in the beginning, if an algorithm is only 10 n squared or n squared, if we are using a test machine of whatever 1 nanosecond, I remember, for 10 nanoseconds, and if we are talking only about kilobits of memory, we are talking about 7 minutes, 5 minutes, etc. test time, which is it's a lot. So overall has a low fault coverage, yeah. But this algorithm has shown to detect unique faults. What is unique faults? If you have a population of defective chips, I will apply all test algorithms I have. These algorithms will not be able to detect such faulty chips, but when I will apply galloping, I will detect them. Although its overall fault coverage is low, and I will show you some results later on, some test chips later on. So after ad hoc, as I told you, we moved from late 70s to late 90s. And in that case, March algorithm becomes dominant. You see a couple of examples, March plus, these are a couple of examples. They look all the same, but in reality, they are not the same. And everybody sensitizes and detects some faults. But anyways, very important is the test length is linear, right? It's linear. So March algorithm becomes dominant. And of course, the fault models concept was developed. Many fault models were developed, not always based on real defects, sometimes based on theory, on imaginations, but they have been used for a while. Although some of them have never been shown to exist in reality, like what you call inversion coupling fault. Inversion coupling fault is a coupling fault involving two cells, and the assumption was when you write in a cell, another cell will switch the value. If it was 0, it will become 1. If it was 1, it will become 0. We call inversion in the victim cell. This fault model has been used in the community for years, but it has been never shown to exist in the real world. Anyways, after the era of March tests, we moved to what we call fault primitive-based or defect-oriented testing. To give you an example, at Intel, I was then back at Intel, was working at Intel. We did some dedicated work on some specific designs, Itanium processors, and we developed some dedicated algorithms for dedicated defects in the real chips at Intel. We called this algorithm SR for whatever reason. This is an algorithm. So this algorithm was designed to target some specific characterized defects. Another algorithm is what we call March SS. This algorithm was developed in order to catch all possible fault models, static fault models. You remember there was a special fault models, and we developed an algorithm that can catch all of this, right? And then Synopsys afterward optimized this algorithm and come up with what they call MSS. So if you put things together in a perspective, you see now different eras of memory testing. The first era, ad hoc, the March test era, and we saw the fault primitive era. And you see the fault coverage has been increasing steadily, right? So this March SS or March MSS can cover 104% fault coverage, and these are the fault models that people developed. I don't need to discuss them in details, but you have single cell faults and coupling faults. Coupling CF means coupling. They involve two cells, and this single cell, they involve only one cell. So clearly, for example, you see that galloping, in terms of fault coverage, for these faults, it detects almost 60%, not 100%. Scan, only 25%. Remember this, 25%, 60%. If you go to March SS or March MSS, they cover 100%. So what I did some time ago is I convinced Intel and ST Microelectronics and Intel, right, to perform the same experiment on different chips of Intel and chips of ST. So of course we barely find test results, by the way, silicon data. We barely find them, right? But I was lucky to convince the two companies that they will do this experiment and publish some results. So what you see different algorithms. So scan, split, etc. You see galloping column, galloping row. Remember, galloping is expensive, is n square. So what we did, we changed galloping instead of n squared to n root square n. So you see the test length now. So what we do, instead of reading the whole memory in the loop, we read only a column. So we go to the base cell, and then we read with the pinpoint read through the column or through the row. And the same thing from working. And by doing that, we reduce the time complexity from n squared to n root square n, because R is proportional to the root square of n. So actually, we reduce the test time. And you see here what we do: fast row, fast column. Remember, different data background, solid, checkerboard, column stripe, row stripe. Why we don't select everything? Based on the experience of the companies and the silicon results. So this is not interesting for scan. These are essays. So we selected what is very interesting. And we wanted to experiment with these blue things. And for these blue things, we did the whole, we experimented, actually, we included all the compilations. So for example, March row, we had 8 versions of the algorithm in the implementation, in the real program, in test program, to test the in silicon. So 1, 2, 3, 4 for fast row, and 1, 2, 3, 4 fast column. And let's now take a look at the test results. So these are the test results from ST, the ones I was allowed to publish. So it was 0.13 micro, so an old technology back then. So, and we published the results for low VDD and low speed. Don't ask me why, that's what they allow me to test. So very important, we had from a huge population of chips, we tested 1135, we had 1135 failing. So a huge population, I cannot disclose, of course, the number. But from that millions of chips, whatever, 1135, we're failing all tests. So this set of tests, whatever test you apply, you will catch the faulty test. So actually applying one test is enough to catch all this faulty. But we find 60 faulty chips which fail only some tests. So which means what is very important for us, these 60 faulty chips, the rest is irrelevant. And if you go and see the fault coverage of the 60 faulty chips, which fail some of algorithms and some not, this is the fault coverage, right? You see them. So the best one, for example, you can see the best one was March G minus, March C minus, March G, March Rho, March SR, and March SS. Quite remarkable. But if you say very remarkable is that we find some test algorithms like March G and March SR and March SS. If you remove them from the test program, some faulty chips were not detected. That's what we call unique faults. For example, March SR was detecting 2 faulty chips. He was the only test algorithm detecting 2 faulty chips. If you remove this algorithm from the test program, these 2 chips will escape. And that's very dangerous. March G was detecting 1 unique chip, faulty chips, and March SS, 2 unique chips. So, and here is the dilemma. We developed the March SS, which actually covers the whole fault coverage. So normally this guy should be enough to catch everything. No, that's not true, because the silicon data shows you that March SR detect 2 chips, faulty chips, that cannot be detected with March SS. Therefore, clearly, the fault models we are considering, they don't model the whole real defects. Meaning that there is a defect mechanisms which are not modeled by existing fault models. That's for ST results and for the best union utility to algorithms. So if you go now to Intel results, and for Intel, we're allowed to publish high VDD and high speed test results. Again, here what you see from a whole population, we find about 1343 fails all tests, and 200 faulty chips fail some of the algorithms and not every algorithm. So these 204 unique or faulty chips are represented here according to the used algorithms. You can clearly see that the best test algorithm from this 204, for example, March G, March Rho, and March SS were the one realizing the maximal fault coverage. But they don't detect 204. They get about 185. So we are still missing a component. Okay. So even though if I can again use March test SS, which is supposed to detect 100% fault coverage, this guy will not catch all the faulty chips. Remarkable enough, and the best union was realized if you combine galloping with either with March G or March SS. And you go to galloping was detecting 9 unique faults. So these faulty chips are detected only with galloping. If you remove galloping from the test program, this will end test escapes and will be sold to the customers who will complain later on. Even though scan, which is an easy algorithm, write 0, read 0, write 1, read 1, when used with a certain stress combination, it was fast, raw, with checkerboard, the guy was able to detect a unique failure, which means if you remove scan from the test program, this chip will escape the test program. So clearly, we have something to explain here. So clearly, traditional methods, traditional fault models break. Fault models make things tractable, but do not perfectly represent the reality. So what typically we optimize? We optimize the test time, the cost, the test patterns, algorithms, but what we do miss is the real condition. How good is the fault model reflecting the real silicon? How good is the fault model correlating with the real silicon? And that mismatch is causing us trouble. Therefore, we used to optimize for test efficiency, time, and fault coverage, but we don't know about how good, how correct are the fault models. And this is why we started again having the test escapes. Our community again is complaining about increasing number of test escapes, partially because of over testing, right? Because over testing, you may start doing more and more and more testing, more algorithm, more voltage, I don't know, more speed, more data backgrounds, but you don't know. Actually, you are increasing the cost, but you don't know how much you are detecting, and maybe you can kill good chips. That's a high risk. Or maybe you can end doing under testing, which means may end also in test escape, and therefore have a problem with your customer. So clearly we have a problem. And this is very good in line if you see the history of testing. Initially in 50s, when we had the first chips of logic as well, people were used to use functional testing. And the most known fault model was to cut fault. So people started using functional testing because functional testing becomes expensive. People moved to structural testing. I'm not talking about logic, not necessarily memory. So each time they come up with another fault model: bridging, transition fault, stuck open fault, in detect, seal aware. Each time there was a need, there was a community was happy at a certain time. Then technology scales, complex chips. Escapes started having escape, and again come up with something new. The state of the art today is what you call self-aware test for logic. But what is very important, people now are going back after structural testing. They are also using functional testing with the hope to compensate for the potential missing faulty chips using structural testing. So functional testing is coming back again, and this is very expensive, and we have a problem. And the question is what to do. Even though recently Google and Meta, they announced publicly that the data centers, their cloud, they suffer from hardware failures. This picture I took 1 year or 2 years ago at the International Test Conference that was presented by Meta, showing that their science data corruption, almost 80% are suspected science data corruption, and 80% of these root cause are related to hardware confirmed failures. And hardware could be your logic or could be your memory. So we have something to explain. There is something that we have to test, which is not tested yet. And this is a major concern. The situation becomes even the worst when we are considering emerging devices or emerging memories. For instance, to give you an example, if this is a device, it could be a transistor, whatever it is. Typically today, what we have been doing today, we assume that we can model a defect as a linear resistor, either in series or in parallel with the defective device. And of course, the relationship with the resistance, the voltage for the model, electrical model, is constant. So what we do this electrical model, and we perform spice simulation and see what will be the behavior. However, this is a measurement we get through our partner IMEC. You can clearly see this is the behavior of a good device. This is the behavior of one of the defective devices. You see, there is no way to present something complex like this one with the linear resistor. So clearly we have a serious gap, and as a consequence, you may end having fault models which are not related to the real defects. Means you will have inappropriate fault models, and therefore you may have test escapes and waste of test time because you are testing for something which does not exist. And what should we do? We should come up with something which targets realistic faults and therefore close the gap between the real defects and the abstraction. And this will allow us to reduce the escapes, but also to optimize the test program. So we need a new paradigm, new test approach. So you can see, you know what? How to solve the issue? I can do hard testing, add more test algorithms, add more, fault models that I can think of, add more patterns, and this course, of course, test cost, add more test conditions, more voltages, more speeds, I don't know what. This means actually the test cost will for sure increase, and you may or you may not detect additional faults. So your escapes may or may reduce, or may not reduce. However, what you need to do smart testing. What is smart testing? You should understand and come up with realistic fault models. You need to understand the real defect mechanisms and how they behave at the functional level and model that behavior. Mimic the real behavior of a defect and apply the appropriate and optimized test pattern which are dedicated for this faulty behavior. Which means actually you need also, when it comes to testing, to put realistic test condition, typically coming from the mission mode or the way you're going to deploy your chip. And this means actually it's a practical solution because we are targeting well-defined defects, and we are optimizing our test program for well-defined defects. And this could be also very, very useful for your learning because a defect may have a unique signature. So even though once I will say the signature, I can exactly say that this faulty chips suffers from a certain defect E, B, or C. And to deal with this, we came up with what you call device-aware test. And that's actually what I told you, an innovation we created in Delft since 2019, something like this. And we have been working on that in collaboration with different partners. And recently we get a European Innovation Council transition grant to spin off a startup company from Delft. And we are working on this. We are building the team and we are starting the company. How does this work? Actually, nothing spectacular. So what we do, we start with a faulty chip. We do what we call device-aware defect modeling. So we really connect the model to the defect. So we come up with a defect, with a compact model for the defect, and then we do the fault modeling. So how we do the fault modeling? We replace the defective device with a compact model that mimics exactly the fault behavior of the defect. And then we're in the simulation. We derive fault models, which could be static, but it could be also timing related. It could be weak delts, which are reliability related. And finally, we generate the solution, which could be an algorithm, which could be designed for testability design. So we can change the design in such a way to make some hard to detect faults, easy to detect, and so on. So it's a complete flow that helps us to detect faults. So let me go. And the major differentiator, of course, is the first part. Let me show you how the first part works. So the first part, how it works. So let's say we have a device. It could be a transistor, it could be an ReRAM device, an whatever device. And we have another device which suffers from a defect that we observed. So the ultimate goal of this step is actually to go through the modeling. First, we do the physics, very important. We analyze how the defect impacts the technology parameter of the device. For a transistor, the length, the width, the density, etc. Once we come up with this, we have to analyze how what we call effective technology parameters affect the electrical behavior of the device. How does, for a transistor, for example, how does it impact the threshold, the current, etc. And once we do that, so we, of course, we care about the electrical equations. We come up with a model, we call it a compact model. And if we have data, what we do, we actually calibrate the model. We calibrate the model to make it very, very accurate. And therefore, we can, when we create this SPICE model, we simulate this device, we can find exactly the same behavior like the behavior we measured during the characterization of the device. So a major differentiator is to close the gap between the defects and the fault, the models itself. So once we have the defect model, what we do, we can do SPICE simulation, defect injection, circuit simulation. Let's assume this is our circuit. What we do through a complex process with the defect injection, simulation, stimuli, etc. But the key component is we replace this defective device with the compact model we created in the previous step, and we do full automation of analyzing of the way the defect impact the functional behavior. And then we derive fault models. So let me show you then for the emerging memories. So as you know, briefly about the memories, there are many emerging memories like STT-MRAMs, like ReRAMs, like FeFET, like PCM. And obviously these devices are quite complex. They are physical driven. They are not like traditional charge-based, but they are new physical driven. And of course, they will have new unique failure mechanisms. So what we did, in collaboration, before going to the use case, I want to stress the fact that what changes is that these unique devices, emerging memories, they have a non-linear behavior. They suffer from unique failure mechanisms that were known in the past. And this breaks the existing fault models, because these existing fault models were assuming that each defect can be modeled as a linear resistor, which is not practical anymore. And the previous models were too simplistic for the emerging memories and also for advanced technology node. So clearly, we need to do something more. And now let me show you two cases. I will show you how traditional approach fails or fail to detect unique faults in STT-MRAM. and then do the same thing for RRAMs. So STT-MRAM is a new defect. As I told you, these are defects which, which have two ferromagnetic layers. One is called free layer and one reference layer. So when you are writing or reading, you are changing actually the polarization of this free layer. So if it has the same polarization like the different layer, they are in parallel, so it's low ohmic. And if they are opposite, it's high ohmic. And for the RRAMs, the main driver is the filament you create. It's a filament, and depending on the size of the filament, is there wide or thin or partially, you can have a high ohmic and low ohmic if they, and that is actually the philosophy. So let me show you something. So at IMEC, we did the characterization of this STT-MRAM device. So we did two kinds of characterization. We did the magnetic characterization and electrical characterization. For the magnetic characterization, if you compare, you see quite similar thing, but you see something very remarkable. The loop flipped. Here we go this way, and we go. The loop is flipped here actually, right? Horizontally flipped. Quite remarkable. And if you go to the electrical characterization, it's quite the same. And the question is this flipping innocent? Cannot cause any problem or never? Our physical analysis revealed actually that the physics of the device, this is the device, a cartoon of the device, showing actually what we call reference layer. These are fixed with a fixed pin. The defective device suffered from the flipping of this, what we call synthetic antiferromagnetic. So you see this, the polarization is up, but the defective guy has down. This polarization of these two layers flipped for some reason. So the question is, does this impact the chip? Will have a problem or not? So clearly, electrically, when you use the electrical characterization, it seems no problem. But if you see the magnetic characterization, you see that there is some flipping. And the idea was actually to see if there is any impact on the flipping or not. So what we did, first we started using commercial traditional approach. We assumed that the defect can be modeled using linear resistors. We did simulation. So we did we created a simulation model in which we had, let's say, 3 by 3. The victim cell, which suffers from what defects, was in this cell. So, and then we go through this, kind of a flow for simulation. We inject the fault, we provide stimuli, we run the simulation, do the simulation, and we find some faults, like you see, for example, here, transition faults, which means we're writing one in the cell, but the cell will fail to go transition operation. So we're not able to write 0, 1 in the cell. We call it transition file. We fail to make a transition operation, either down or up. We fail, but also sometimes we perform read operation to the cell, and we get raw read value. So here, we are applying read 0. The cell contains 0, but it gives us 1. So this is the fault models created by the traditional approach. So easily we developed an algorithm. That's the algorithm, and we applied the algorithm to the good device. The good device passes, of course, nothing happened. We apply write 0, and then write 1, and then we read 1, and then we write 0, and then we read 0. Everything fine, goes fine. And then we applied the same algorithm to the faulted chip, the guy who has these ferroelectric layers, flipped. Also, the algorithm passed correctly, no problem. So according to the traditional approach, no problem. Both devices are good. So normally we'll ship the device to the customer. But let's see what happened when we used our approach. When we used our approach, actually, I will skip all the details about the defect model, etc. So that is the result of traditional approach. Our approach showed something very remarkable. Our approach showed that when the neighbors are all set to 1, and we apply, this is CD1, 1, 1, these are the state of the neighbors, right? All the neighbors are 1. And we apply to the defective cell, which was initially the 1, we apply 0. What happened is that this sometimes fails. Not always, sometimes. And here is the diagram. This is actually the distribution of a defect-free, and the orange is the distribution of defective chip. So about 11 or 12% of the cases, we fail to perform one write 0 operation, which means transition write operation. Changing the state from 1 to 0, in about 20% of the cases, we're failing. And this could give you a problem in real chips, in real field. So this you will never catch using traditional approach. With device aware test, it gives you inside information that you need to do something about. So we give it a name, we developed an algorithm, and we optimize it. So here is an algorithm we developed with kind of hamming. Now we repeat it many times because it's probabilistic. And you can also actually play with the hamming, how much you're going to ham the cell, and to increase the coverage, the probability of detection of the fault. Actually, what we did more, we actually, even though I applied a magnet, that's actually the insight we learned from device aware test, in order to guarantee 100% the detection of this fault. By applying a write operation remotely through a magnet, any device suffering from that problem, the SAF issue, we were able to detect it 100%. So clearly, for STT MRAMs, the conventional approach fails and device aware test can work. We did the same thing for ReRAMs. These are devices we get from ST Microelectronics. These are characterization results. You see, the blue is a good device, and the orange or red is the defective chip. Here you see clearly there is a strong fault. But here you see that sometimes the state set was actually what we call disturbed one. So it's kind of a weak fault. What we find in the characterization, so it's about 1% of the cycle will affect it. And the fact you do apply the operation in 3 cycles, the memory was affected, and then the impact will disappear, and normal. So it was kind of intermittent. You apply it, and then you do it, and then it disappears. And therefore we call it intermittent undefined state, because this is kind of an undefined state. It's not 0 or 1, because if it's 0, it should be here, and if it's 1, it should be here. Okay, so what we did, we applied the traditional approach, which assumes that every defect can be modeled with a linear resistors, and we applied our approach in which we developed a physical model. So I skipped the details, and then we compared the result. These are the faults that can be sensitized, or fault models developed by our approach, and these are the fault models developed by the linear resistor model. Clearly, the linear resistor model, gives you fault models which are not related to the defect at all. So you will be testing non-existing problems, and therefore you have test escape, and you will waste your time. Meanwhile, this approach will allow you to catch realistic defects. Again, I skip details. I will just give you an idea. And this will help you to develop appropriate test algorithm, because you know the behavior, and because it was intermittent, you know that the detection probability, the detection is probabilistic. You can, improve the number of the hammering you do, from writing you do, in order to increase the fault coverage. Or you can think about developing a DFT, design for stability, which means changing the design, putting some hardware in the chip in order to facilitate the detection of the faults. So this makes your life, actually, it gives you a lot of inside information in order to improve the outgoing product quality. And maybe you can think, now we need to use error correction codes, because this for intermittent faults could be easily detected and even though recovered by error correction code. So we demonstrated this approach for many, for different technologies, STT-MRAM, ReRAM, FeFET, for different unique defects, like you see, for example, STT-MRAM, back hopping, contact, interconnect, many defects. And you can find all, for those who are interested, these are different publications we published, date, ITC, different years, etc. So you can go back, and if you are interested, you can go and read them. And actually, at the moment, we are demonstrating the device aware test on logic or AI chips, and we are progressing there very well, and hopefully in the near future we will report something about it. So what is the future outlook? So physics aware testing is a must to have, at least in order to reduce the escapes. There are models, fault models, traditional fault models, which do not catch the real world. So we need to do something about it. Very important. So we need to link the fault models to the real silicon, right? And therefore we need kind of cross-layer understanding, even though the way we test our chips should be actually coming from the real application, right? In order to try to mimic what can take place in field. And we will see a lot of directions towards what we call adaptive intelligent testing. AI now is driven everything. So AI also come in testing. To optimize things, but also to provide good feedback, to do in-field learning, but also to optimize our test solution and do some prediction. And very important also is that in-field monitoring and self-repair is and has become more and more important, especially now you have a device which would probably start dying in field, and it's very important to do what we call life management of the chip. Once at the moment you have let's say a monitor or a sensor, you start detecting that the chip starts fading, you have to do something about, for example, either repair it or lower the frequency or whatever in order to ensure that you will meet the lifetime of the chip. So in short, we are actually evolving from past failed screening to more continuous reliability assurance and management in field. To close my presentation and then have some time for discussion, so memory testing is a physics problem, so we have to deal with actually also logic. We have to deal with the real defects. We have to care about that, and it's becoming more and more important. So current methods are reaching the limit, and innovations should take place. Device awarded is one of the scenarios which we can go, and clearly we will see a paradigm shift in the community coming soon in order to ensure the quality and reliability required to market. Again, the fact that Meta and Google publicly announced this science data correlation, created a lot of discussions in the community, and many teams around the world are working on improving this. Before closing, I would like to thank people with whom I have been collaborating in this device award test, from Delft, many PhDs, many master students, but also from Polytechnic de Torino, also from Broadcom, also from Marseille, and also strong partners that they have been collaborating not only in this but also in different projects. That's IMEC colleagues from IMEC. I would like to acknowledge and thank all of them. And again, as I mentioned, we are now creating a startup. After we get this funded money or the funded project from European Commission, and we are now starting this project called Popcorn, which will end, of course, in a startup. So if you want to know more about it, just go to this website, popcorn-project.eu. That's all, and I will be happy to take some questions if you have any.